Welcome to The Explainer. Today, we're diving into something we see all the time, a simple pot of boiling water. But don't let that fool you. Hiding inside that pot is a secret battle between temperature and pressure, a battle that doesn't just explain how we cook, but actually how we power our entire world. So, let's kick things off with a real head-scratcher. Why is it that a pressure cooker can whip up dinner in just a few minutes, but if you try to cook that same meal on top of a mountain, it takes forever? It seems like a total paradox, right? Well, the answer to both questions is hidden in what's really going on when water boils. To crack this, we gotta think small. I mean, really small. We're gonna follow the journey of water molecules, step by step, as they get hotter and hotter. Their story holds all the clues we need. Now, this journey happens in 5 distinct stages. We're going to watch our water go from just a cold liquid to the absolute brink of boiling, right through the chaotic process of turning into steam until finally it becomes something else entirely. So, let's start at the very beginning. Stage 1. Super simple. We have a pot of water. That's it. Now, in thermodynamics, this has a bit of a fancy name. They call it a compressed liquid. But all that really means is that the water is stable and it's nowhere near boiling. It's just, well, it's water. Okay, now we turn on the heat. The temperature starts to climb and climb until it hits 100 degrees Celsius. And then it just stops. Right at that exact moment, the water becomes what's called a saturated liquid. Think of it like a stadium full of people all holding their breath at the same time. Every single molecule has absorbed all the heat it can possibly handle as a liquid, and it's just about to make that huge leap into becoming a vapor. And this right here, this reveals the secret handshake of boiling. See, during this change from liquid to gas, pressure and temperature are completely locked together. They're like dance partners. If the surrounding pressure changes, the boiling temperature has to change with it. At sea level, that dance happens at 100 degrees C. But if you change the pressure, you change that boiling point. Honestly, this one single relationship is the key to our entire mystery. So here we are at stage 3, boiling. And this is where things get a little weird. Even though you're blasting the burner, if you stuck a thermometer in that water, it would stay locked solid at 100 degrees. So where's all that energy going? It isn't making things hotter. It's paying a price, what scientists call the latent heat of vaporization, which is basically the energy cost to break the bonds that hold all those water molecules together as a liquid. And let me tell you, that price is steep. Just look at this number. To turn 1 single kilogram of boiling water into steam, it has to soak up over 2,200 kilojoules of energy. That is a huge amount of hidden energy, all getting poured in while the temperature doesn't budge one bit. Finally, after all that energy has been paid, the very last drop of liquid just vanishes. We're now at stage 4, saturated vapor. This is steam that's basically living on the edge. If it loses even a tiny bit of heat, it's going to immediately start condensing right back into water. But what if we keep adding heat? Now that the change from liquid to gas is totally done, the temperature finally starts to climb again, soaring past 100 degrees. This is superheated vapor, a stable, dry gas that's no longer on the verge of collapsing. Our journey is complete. Okay, so that was a lot to keep track of. How do scientists possibly visualize this whole process at a glance? Well, they don't just describe it in words. They actually draw it on a map. This map is called a TV diagram. I know, it might look a little technical, but it's way simpler than it seems. It just plots temperature going up against something called specific volume going across. And specific volume is just a fancy way of asking how much space does our water take up as it expands from a dense liquid into a fluffy gas. And here's the really beautiful part. Our entire 5-stage journey, from cold liquid to that flat boiling zone, all the way to superheated steam, it traces a clear, predictable path right across this map. Every single step we just took corresponds to a specific neighborhood on this chart. Let's see how this map solves our mystery. Now we have everything we need. We understand the journey and we've got the map. So let's go back to that mountain and that pressure cooker, and finally, let's solve this thing once and for all. And it all comes back to that special dance between pressure and temperature. On top of a high mountain, the air pressure is lower. And because pressure and boiling point are locked together, lower pressure means a lower boiling point. Water up there might boil at just 90 degrees Celsius. Sure, it's bubbling, but it's not actually hot enough to cook your food right. A pressure cooker does the exact opposite. It traps steam, which dramatically increases the pressure inside. This forces the boiling point up, maybe to 120 degrees Celsius or even higher. Hotter water means much, much faster cooking. It really is that simple. But our map here, it doesn't just explain boiling water in your kitchen. If we push the conditions to their absolute extremes, we start to find points on this map where the rules of matter, well, they start to get really, really weird. At an incredibly specific, very low pressure and temperature, we find something called the triple point. Now, this isn't just a theory. It's a real physical state where you can literally see ice, liquid water, and steam all existing together at the same time, in the same container, in this perfect, bizarre harmony. Now let's go the other way, to ridiculously high pressure and temperature. Here we find the critical point. At this threshold, the line separating liquid and gas completely vanishes. The substance isn't one or the other anymore. It becomes this strange thing called a supercritical fluid. Beyond this point, the very idea of boiling doesn't even exist. So after that entire journey, from a simple pot on the stove to the far-out edges of physics, what's the one big idea we should take away from this whole delicate dance between pressure and temperature? It comes down to this core principle of thermodynamics. A substance's properties depend only on its current state, not on the path it took to get there. It doesn't matter if your water was frozen solid a minute ago or was superheated steam. Its identity, its very nature, is defined only by the here and now. And that leaves us with one last mind-bending question. We've seen how pressure and temperature create the familiar states of solid, liquid, and gas that we all know. But what happens if we push those conditions to their absolute limits, to the kinds of pressures you'd find inside a star, or the deep, deep cold of outer space? Well, that is precisely how new, exotic states of matter are discovered. The simple act of boiling water isn't just a step in a recipe. It's the first stop on a map that stretches across the entire universe.